And let me take you to the practice quiz. Question number 1. If f of 16 is 7 and f prime of 16 is negative 3, estimate f prime of 16.01. Okay, 1 more minute on this. Okay, so X and Y axis, the input is 16, the output is 7. We know that the function goes through this point, but how does it go through this point? It must be going through it in a downward fashion, because the derivative at this point is negative 3. Negative 1 would be a 45-degree angle. Negative 3 is more steep. It's kind of coming through like this. Okay. And so f, oh, dog, I keep making these mistakes. I didn't want you to estimate f prime of 16. I wanted you to estimate f, let me retype that, estimate f of 16.01. So let me give you a little bit more time now. I'm going to give you another minute. Okay, so f of 16.01, our best estimate would be f of 16 plus, now if we went 1 unit over to the right, we'd expect it to drop by 3. But we're not going 1 unit over to the right. We're going 0.01 units to the right. And then we're going to drop. So this is 7 plus negative 0.03. Every time it goes 0.01 to the right, it goes 0.03 down. And this then becomes 6.97. Okay. Give me a little feedback. Well, actually, let me go through one more thing before I have you give feedback. This, in general, let's generalize this. F of x0 plus delta x. What we're really doing there is we're saying that that's equal to f at x0 plus f prime of x0 times delta x. Now the reason why this works is, so this was the f prime, and the delta x was this part right over here. The reason why this works is that this is really change in y over change in x, the slope of the tangent line, times delta x. And these two are going to kill each other off, and you're going to be left with the delta y. So this is the change in the y produced by that delta x right over here. All right, so give me some feedback on this one. Exam 3 is not today. Exam 3 is on Wednesday. So 2 days from today. Alright, now let's go back. Alright, this idea right here though, that f of x0 plus delta x is, well, I would just be rewriting this again. It's just this. This is something we're going to expand on today. So it's important as a review activity, but it's also foundational for what we're doing today. Okay. Now, number 2, use the test of your choice to determine convergence or divergence.
Did you start the recording, Mr. Shankin?
I did. Thank you for checking though. So give you another couple minutes. And 30 seconds more. Okay, so before I do this one, I'm going to come over here to yesterday, or last week's lecture. At the end, I had made this kind of a flow chart. And when you're asking, does a series converge? First thing, divergence test. And this one, let's pop back to here, clearly passes the divergence test because the denominator is getting huge quickly. K factorial is one of the fastest growing. It's way faster than even an exponential function. And the top is just a linear function. So it's driving to 0, passes the divergence test. And then, is it a known series, geometric p-series, or essentially one of these? No, because of that factorial thing, it's nothing like what we're used to. Okay, so then, the integral test, if we can integrate it. With factorial, no way. So, then we go this direction. It's either the ratio test or the root test if the ratio test doesn't work. Usually we do the ratio test first. Alright, so that's how I kind of got to the ratio test. So I state the name of my test. And if I have trouble getting oriented on any problem, I write out the first, 3 or 4 terms of the series. So the ratio test, I'm going to have to get the limit as k approaches infinity of a sub k plus 1 over a sub k. And a sub k is just what's there. So a sub k plus 1, we just substitute k plus 1s for the k's. Like this. And so this is going to be this top one divided by the bottom one. But I'm going to copy dot flip, so I'm going to flip the bottom one. And then I need to reduce it. Well, I'm supposed to have a limit. When I reduce it, this 14 and this 14 divide top and bottom by 14. And then is k plus 1 factorial. Like it would be like 100 factorial. And this would be like 99 factorial. All the numbers would cancel out except the highest number, which would be on the bottom. Okay, so this is equal to the limit as k goes to infinity of 1 over k times k plus 1. And this thing, the numerator is stuck at 1 while the denominator gets bigger and bigger. So this limit is clearly 0. And on the ratio test, we didn't have to get 0. If we'd have gotten any finite numbers, alright, so ratio and root test. Let's go back to the ratio test. There's the root test. There's the ratio test. This r that we get from this, if it's less than 1, the series converges absolutely. It's like the thing you multiply to get to the next term. So it's essentially acting kind of like a geometric series with an r that's getting really close to 0. And so since r is less than 1, the series converges. Okay, give me a little feedback on number 2. Can't you also factor out that k plus 1 in the denominator as well? I'm not sure I understand that question. Oh, this k plus 1 could have canceled. Oh. That's right, there was a k plus 1 in the numerator that this one that I had overlooked. I was just seeing this and this one, and then these reduce. So we get 1 over k, but that limit is still 0. So thanks for pointing that out, Rowan. Alright. Now, let me take a break for an announcement here. This is our second to last regular day of class. So, last day of class is Wednesday. Wednesday, we have an exam. For the first half hour of class, I might need to be finishing this section 11.1. And if not, we'll at least be doing some review in that first half hour. And then you'll be taking exam number 3, covers 10.1 through 10.8. And then the final exam is on Monday, December 7th. Also, I hope every one of you is moving on with me to Calculus 3 next semester. It'll be the same times, Monday, Wednesday, starting at 5:30. I want to inform you of a new policy that I'm going to have, a new testing policy I'm going to use with all of my classes next semester. And I had some unusual things happen this semester. I had a college algebra student who never came to class, who got perfect scores on homework, and actually one of the problems, calculus was used to get the answer. And so I realized I needed to put a little bit of accountability into the testing procedure. So this is going to be the new test taking procedure. Soon after the exams, so this will be next semester in Calculus 3. Soon after the exam is started, I will send a message in Discord to some semi-randomly chosen students stating that we will individually connect via Zoom, not via Discord, because Discord, it's a little harder to share screens like this, for perhaps 10 minutes during the exam. During a Zoom session, I will ask the student to do a problem and explain their work. Students point their cameras at their face, place hands on their chin, and they tell me what to write. And as they tell me what to write down, I write it down and the work shows up on both of our screens. If the student cannot do the problem, I may ask for more problems to be done. Student selection is random, but students who have participated little in class have a greater likelihood of being chosen. And so that's what will happen in Calculus 3. The Calculus 3 material is rather independent of Calculus 2 material. It is rather dependent on the basics of stuff in Calculus 1, but is rather independent of the stuff in Calculus 2. Any questions with regard to this? Okay. And another announcement is if you there was an announcement posted in our Canvas today that was a math department activity that's highly encouraged, and I'm giving extra credit for it, and so please check that out. And also after the break today, I'm going to write up a little reflection thing for some more feedback that I need from you. So we'll do that right after the break. Alright. Also, you may have gotten an email asking you to rate your instructor for this course if you check out your SFCC email. I need to tell you that that's very important. It's one of the primary ways we improve instruction at this school. And the data that I get from that is after the semester's over, and I just get the comments and just the total data. So you're anonymous with that data. All right, let's go to the next one. So the instructions are the same. Use the test of your choice to determine convergence or divergence. Do part B. So I'll give you another minute. Probably don't have time to totally finish it, but just get as far as you can. Okay. So when I look at this, I see that, let me jump to this flowchart. We ask, does this thing converge? Well, first of all, does it pass the divergence test? Yes, the numerator is fixed, so the denominator gets bigger and bigger, so the sequence goes to 0. Certainly passes that. Very quickly look at that, and then I go on. And then, is it a known series? This one is. If it didn't have this -4 there, and this 6 gets to come out in front. It's one of the properties of series, and is that 6 would just factor right out. If it didn't have that -4, this is the p series. With p equals 3, and so it converges. But because of the -4, we need to use either the comparison test or the limit comparison test to show that it converges. Now, when you make the denominator smaller by subtracting something, it actually makes the fraction bigger. So we can't use the comparison test. We'd have to use the limit comparison test. This is a p series. One of them is a p series. We'll call it doesn't matter which one. And you can do it 1 over that or 6 over that. Let's do 6 over that. And this we know it converges. Because p is equal to 3, and as long as it's greater than 1, it converges. And then b sub n is this one. And so what we do is look how different this is. The ratio test is a sub k plus 1 over a sub k. This is and it's a limit of that as k goes to infinity. This is going to be a limit as k goes to infinity, but not comparing the test with another portion of itself. You know, this is two different parts of a. This one is comparing two different things. So you take the limit. As k goes to infinity. It doesn't matter which order you put them in. A sub n on the top, or b sub n, a sub n over b sub n. And this time we don't have to get it less than 1. We just have to get it not to be 0 and not to be infinity. If it's anywhere not 0 or not infinity, then these two things have to converge or diverge together. And then this one converges, so we'll get that one to converge. So this is the limit as k approaches infinity, 6 over n cubed. Now the b sub n is copy dot flip. It'll flip over n cubed minus 4 over 6. And the 6's reduce to divided by 6. And as k goes to infinity, we can say that this whole thing, this is horizontal asymptote theory. The degrees are the same of the polynomials. It's also the theory that we look at the associated function, because this is only defined for k equal 1, 2, not for the fractions in between. But this limit will be the same as the limit of the associated function, f of x equals this. And so this is clearly 1. And we might have to say because, a little justification, because both are the same degree, the limit is the ratio of the leading coefficients. And it's horizontal asymptote theory that we're using. And then we make our conclusions since, now this is the comparison test. Let's go back and review that a little bit. Comparison tests. Limit comparison test. If, as long as the limit L, we call this thing L, is not 0 or not infinity, then they both converge and both diverge.
Can we use the integral test of this one too?
Which test?
Integral.
Integral test.
Yeah. Because I don't know.
If you think you can integrate this, hold it. It's not. It's this one. Do you think you could integrate that? That would be a tough integral from 1 to infinity. Of integrating that one, you'd have to do like a partial fraction decomposition or something, and it doesn't really factor, and it would be a mess. So no, I wouldn't want to use the integral test. If this had an n squared on the top, then the u would be n cubed minus 4, and n squared would be on the top. Then I could integrate that easy, but the way it is, no.
Can you write it down?
What that integral?
If what kind of we can use the formula integral.
The integral of 6 over x squared, x cubed. Minus 4 dx from 1 to infinity. That would be the integral that you'd have to evaluate. So you take exactly that expression, you just substitute x's in for that. And then let's look at the integral test. The integral divergence test. There's divergence. There's the integral test. It says then this and this both converge or diverge. They do it together. And this thing, you got to get something finite, not something infinite. But here, this is too hard to integrate.
I mean, what kind of form looks like so we can do the integral?
If this had an n squared right here, then you could do that, because then you'd take the u being n cubed minus 4 du, well, not n, it'd be x cubed. and then du dx would be 3x squared. And you see that would show up in that one you could integrate. So
Thank you.
You're welcome. So that one, again, on this flow chart, integral test, only if it looks like we could integrate it. So we're gonna use that as, all right, so then, all right, so.
Oh, one more question.
Yeah.
If in the denominator it's 6n squared, so can we still use the limit comparison text? You just change it to 6 to 6n squared on the top, right?
Right.
Can we still use the limit comparison text?
You could with that one, and that one will diverge because that's essentially the harmonic series. And you could, the b sub n would be the harmonic series, like 6 over n, and then you'd get a finite number.
So is it a lot can use the integral test? You can also use the comparison text.
Yes, there's a number of them can be, you would have your option. A number of different tests would work. But some of them, only one test would be appropriate. Like this one right up here, the ratio test, I think this one, when it has a factorial in it, the only test that's going to really work is the ratio test. Like if it had that n squared, you could use a limit comparison test, or you could use the integral test. All right. So I don't think I had you give me feedback on this one. Give me feedback on B. So there's a question, is homework 9.2 optional? That's something that we skipped. Yeah, I'll give you a little bit of extra credit if you do the 9.2. And the answer, does it matter which fraction a sub k or b sub k goes on top or bottom? The answer is no. The reason why it doesn't matter is because we're not trying to get that limit L to be less than 1. We just have to have it be anything that's not 0 or not infinity. And then those two series will converge or diverge together. So that's why it doesn't matter which order they go on top and bottom. Okay. And state the ratio test from memory. Just the essence of it. You don't have to get all the particulars, and just the idea. Don't look it up. 30 seconds more. This is the limit. As k goes to infinity, a sub k plus 1 over a sub k. The next term divided by the current term. And it's when you divide this, you're kind of getting that common ratio in a geometric series. If it was really a geometric series, you'd get that common ratio right here. And we call it the same letter, r. And same conditions as the geometric series. If r, now we're going to wind up using this most of the time with all positives, but I can still put absolute value. Plus 1, then the series converges. And that's the essence of the ratio test right there. Just figuring out what the r is, seeing that it's like a geometric series, same conditions that the geometric series has. Give me a little feedback on reviewing the memorization of the ratio test. That's a value you could leave out. Most of the time we don't use it. We usually use it as an absolute ratio test. Alright. And that's it for practice quiz. And questions on homework? Or on anything else?
Could you do number 39 on for 10.7?
10.7. Number 39. Page 699. Okay, and the directions were choose your test, use a test of your choice, determine whether they converge, and I also want you to say absolutely or converge conditionally or diverge. Right, so we look at this one, and what I notice is that if this plus 1 was not there, then, and that plus 1 makes very little difference, you know, as k gets really, really big. If that plus 1 wasn't there, this is essentially k cubed over k to the 4th, which is 1 over k, and it's alternating. Now normally this would be a diverging series because it's the harmonic series. It's essentially the harmonic series. Which diverges. Except it's got this alternating sign deal. And so this thing passes the divergence test. The limit of this is equal to 0, because the denominator has higher degree than the numerator in its essence. And it alternates by the alternating series test. Now the alternating series test, there it is, alternating series. Okay. There's this one condition 1, but the main thing is this one. Alternating series converges provided that the limit of the sequence is 0. So the alternating series test, this series converges. All right, Kylie, does that answer your question?
Yeah, when it said to choose between the two tests, I thought that we had to do it by root or ratio test.
Ah, okay. Also, it says use the test of your choice. So it's all the tests that we've had so far. And then we also have to say whether it converges absolutely or converges conditionally. So this one, we do need to say it.
I thought that was for 10.8 that you get to choose your tests. Since this is for a root and ratio chapter, I thought that you had to choose one or the other.
So this was 10.7, which is the root and ratio test. You know, no, you don't have to. But if you, they weren't clear on that though. I can see why you'd make that conclusion. But if you did use a root or ratio test on this, yeah, actually, I think that would be pretty complicated. I don't think I'd use one of those. Yeah.
I saw when we use the alternative series text,
Yes.
we have to get both. One is absolute value and the other is the original value. Both converge. Then the next serial will be converge absolutely. We have to use the absolute value. So
The alternating series test.
if absolute value is converging, then it will be converge absolutely.
I think you're making the alternating series test more complicated than it is. It's really, really simple. Alternating series test, really just focus on the second condition.
But I saw the book now has the definition for absolute and condition converges for the alternative serial. So in the book, I just saw the book, so following the step.
All right.
So,
In the book, they'll pay a lot of attention to this first one. The terms of the series are non-decreasing, and they'll make sure that that's satisfied. And that's very rarely does that make a really big deal. So I don't emphasize that. But yeah, I don't think it's worth paying much more attention to that.
Okay, thank you.
You're welcome. All right. Any other questions?
Can you do number 13 and 10.8?
Okay, I'll try to be real quick about it though. I might just lay out the basics. 10.8, number 13, that's page 703. Alright, so this one is going to, I know it diverges because one, if you replace this with something larger than this, it still diverges. And then this has to go to 0 pretty darn fast. I mean, go to infinity to make the fraction go to 0. This has to go to infinity faster than this goes to infinity, but this goes to infinity way slower than this goes to infinity. This one is essentially the harmonic series. This one diverges. So this one is going to also diverge. But how do you pick the right test so that you can show it? All right. So again, the flow chart, it passes the divergence test because the bottom keeps getting bigger and bigger and the top's stuck at 5. Okay. And back to the flow chart. Is it a known or essentially similar to one of these? We could possibly do a comparison test with the other one, or we can go integral test or ratio test, or root test. Okay, and now if you tried to think of the integral test on this, the integral, you'd have to set your u to be 2 plus ln k, but then you'd get a 1 over k. If this had an extra k in its denominator, then I'd be interested in using the integral test, because then it would be easy to integrate. But like this, it doesn't look like it's very easy to integrate. So I know it's diverging because it's slower than this. How do I prove it? This one is a little tricky. I can't think of anything right now. Anybody have an idea?
Can you?
I used the limit comparison test.
Between
I compared it with 1 over the ln of k, and then through some kind of squirrely comparison, I determined that 1 over ln of k diverges, and then because it's like greater than a known divergent, it also.
That's right. That's this. We can say this diverges because of the comparison test. Not the limit, just the comparison.
I use the comparison test, but I keep the 5 on the top. Still say it's converged. Is it okay?
All right, hang on. Let me finish what I'm writing, and then because I couldn't write and listen to you at the same time, so I'm gonna have you repeat that. But wait till I get done writing. Diverges because of comparison test with this, which diverges. All right, repeat what you were saying again, Yoon.
I do the same thing. It's 1 of, but instead of 1, I was using the 5. 5 divided by lnk.
That's fine. That's fine. You can use it 1 or 5 because when you do those limit comparison test, it will be you just have to get it not to be 0 or not to be infinity. So it doesn't matter whether it's 1 or it's 5, whatever that limit L turns out to be. All right. So on this one, so who was it that was telling me to use this? That was talking?
That was Rowan.
Rowan. All right. Rowan, how did you go from here to using this? You did some step in between?
Okay, well, so basically I assumed that the sum, if you got an infinite series, which is the ln of k,
Yeah.
all of the values of that series are going to be less than the series of just k. So then if you divide both of those terms by 1, you flip the
between these two, you use the limit comparison test. Okay, so the idea is between these two, you use the comparison test. And then between these two, you use the limit comparison test, and then you got it all. All right, so we're going to stop with that on this, and we'll start again. At 6:45 p.m. Take a little break. Anybody need to speak with me individually before I take my break?
Yes. Yes.
Go ahead.
For the question 39, we just talked about. You say it's harmonic serial, and but instead of when we do the alternating serial, for the harmonic serial is divergent, but for the -1 and 2k plus 1 it's converge. So if we do that, it will become converge. It will become converge, but I don't understand why you write conditionally on the
Okay, conditionally means the other way that it can converge is absolutely. And it would only converge absolutely if the absolute value of that also converges.
Yeah.
And so
do we need to testing out the absolute value too?
Say that again, I didn't understand that.
So do we also need to do the absolute value too?
No, we don't need to. We just need to think about it. If it didn't have this, if it had this absolute value, it would not converge. because then it's the harmonic series,
Oh, yeah.
essentially.
How many?
Okay?
Oh, got
And
it.
so
Okay.
when it would not converge, if it had absolute value, then it only converges based on the condition that it's alternating. So that's why it's converges conditionally.
Oh, okay.
Okay? But it does not converge absolutely because that would, with the absolute value, would not converge.
Okay. Okay. Got it. Thank you.
You're welcome. Anything else? Anybody else need to talk to me? All right. Thanks. Really appreciate it, Bill. Okay, we shall start again. And we're going to 11.1, approximating functions with polynomials. And an alternate title could have been Taylor series. And by the time we are done today, we will be able to write something like sine of x as this. Sine of x is equal to x minus x cubed over 3 factorial, so on. That's a pretty amazing thing that we're going to be able to do by the time we're done today. If I finish this section. I might have to finish it on Wednesday. We use an infinite series, and only if it's convergent, if it's a convergent infinite series, to replace another function. So we could replace sine of x with this when the function is too difficult to work with. So in practicality, we wouldn't use it to replace sine x. Sine x is easy to work with, and we have a calculator to use, and so on. With infinite series, with the infinite series, suppose we had a really messy function though, we are able to take the integral, solve the differential equation, create the modeling function. So we might be having to take an integral of something that's just something that is so complicated you can't take the integral. But we could do an infinite series to replace it, and it turns out if you take the integral, it's a crazy thing about this theory. It turns out amazing that if you take the derivative of each side, you take the derivative term by term. If you take the integral of this side, you take the integrals of each one of these terms. And you get so on and so forth. So when you couldn't take the integral of this really messy function, you could take these integrals, which is a piece of cake. And sometimes messy functions come up in differential equations. You can't solve the differential equations. You replace it with its infinite series, and then you can work with it and figure and solve the differential equation. Sometimes you only have data to work with, a whole bunch of data points, and you don't know what the function is that went through it. And when you try to create the function, it's too complicated. You can't create a modeling function. But we are able, in some cases then, to create the infinite series for the function. And so this is what we wind up doing when we get pretty difficult problems, is we jump to infinite series. Now, if I was in your position, I would be in a question that would immediately come to mind, which is, well, nobody wants to work with the infinite series. You're never done. If you're integrating term by term, you're integrating forever, and how in the world could that help you and save you any time and get you any answers? It turns out that we will wind up using series that converge really quickly to these things. And they'll converge so quickly that we will usually only have to go out about 2 or 3 terms. Just take 1, 2, maybe up to the x to the 5th power, but maybe even only x cubed. We'll only have to take a very few number of terms in this, and then work with it, and it'll do an amazing job for us of approximating the function. So this is pretty grand stuff, and it's really why we spent so much time in chapter 10 on getting series that converge. Well, this is only working for convergent infinite series. If the series doesn't converge, you can't use this theory of it. We're going to find out that most series will converge, that we will need to work with, that we'll be able to come up with an infinite series to replace most functions. And they will converge, but just kind of close to a certain interval. And so we will have what's called an interval of convergence. Okay. Now, creating modeling functions was this last topic there. It leads us to this next question. What are the simplest functions that we can model with? Does anybody have a suggestion? What is about the simplest functions that you can think of, that you can model other complicated functions with? Anybody?
Harmonic series?
A harmonic series, but even super simple functions, not a series, but just a function. What is about the simplest?
Like a linear function?
Linear, and then if you want to get slightly more complex, what would you go to after linear?
Exponential?
Now that gets very complex, but linear would be like f of x is ax plus b, and then slightly more complicated, you go second degree, and then next go third degree. So on. And all these are the simplest functions we can model with are what we call polynomial functions. It's about as easy as we can get for modeling something if we restrict ourselves to polynomial functions. And, alright, now a power series is an infinite series of this form. Now, notice when I said that we're going to put like sine of x is equal to x and all that right there is some form of a power series. And a power series has a linear, squared term, a cubed term, all the way on up, and it just has all these different coefficients. Call it C0, C1, and then it's nice to start these with 0 so that the index 1 matches the power on the x, the index 2 and the power. So it's really easy to write it in some summation notation, k and the k over here. Or we do this slightly different with x minus a raised to different powers. And this is a power series centered at A. Alright. Now, this is from the textbook. Viewed another way, a power series is built up from polynomials of increasing degree as shown in the progression. Degree 0 all the way through degree n, until you get the infinite case. According to this perspective, a power series is a super polynomial. Therefore, we begin our explanation of power series using polynomials to approximate functions. All right. Now, here's where I diverge from the book. So, imagine approximating f of x1 plus delta x. Remember, we saw this expression in the practice quiz today. When given f of x for x less than or equal to x1. So, x1 is right here. So this might, suppose this x-axis was really time. If x is time, x1 might be the present time. So we have all this data up until the present time, and of course we can't see into the future, we'll have to project into the future. Alright. So, in these cases, now let me Alright. So, in this first case, let's suppose that we had a line. We got to go through this point right here. Oops. Get that line a little bit better. It's my attempt at a straight line. Alright, so we have a straight line of data coming up to the present time, and we want to project out into the future. So we might say we want to project out to here, x1 plus delta x. So some small amount, kind of like in the practice quiz, you know, you knew f of 17 and you had to estimate f of 17.01. Then what we're going to do is project this out. Project the line out. And then this part from here to here, we go to a different color. Will be delta x. And then the change in the height that happens from here to here is delta y. And in this case, when we do f, we're approximating into the future, x1 plus delta x. Just like the practice quiz, we will take f of x1. Now, if you didn't know what was happening before x1, you would just project out horizontally. Your best projection in the future then is just that it's going to stay at the height of f of x1. But since we have this data from the past, we'll use that. We'll say, it's increasing, so we'll be adding something. But how much do we add? Well, we know delta x, it kind of depends on what the delta x is. If the delta x is, 0.01, you're not going to add very much. But if the delta x is, 6, it's going to be, way out there. What do you multiply the delta x by? Well, you multiply it by the change in y over the change in x. Because the delta x's would cancel out, and you'd get this plus the change in y, so you'd get the appropriate height plus the height that you're supposed to have to add to this. And this is the same as f of x1 plus f prime at x1 times delta x. And this would give you the exact answer if your data had been on a straight line and continued to stay on a straight line. We'd be able to project into the future that way. But in the future, we never know for sure if it's going to stay the way it's been going. But that'd be our best guess. Right. Now, situation B. In this case, let's pretend now that we have a function going through that point, but it's going like this. Okay, now into the future, we don't know what it is, so once again, we have x1 plus delta x there, and what's going to happen is the real thing, the real function may well go like this. But what we're going to wind up doing is we might, if we only use the first derivative, we'd project along a straight line. Let me kind of blow it up here. We project along the straight line, which is going to be, let me get that a little bit better. Which is going to be a pretty decent projection. But since this thing was curving upward, concave up, the slopes kept increasing. So when we just took the last slope, we're going to be a little bit of an underestimate right here. So here, f of x1 plus delta x is f of x1. Projecting it in the future, take your previous height, f of x1. But the last slope that we knew, it was going up. Well, we know from what we just did, we use f prime at x1 times delta x. But we know we're going to get an underestimate because it was concave up, and this thing, the slopes are continuing to get bigger. So what we would do is we would get a better estimate even than this, and we would kind of bridge the gap between that red dot there and the real curve up here if we could use, well, look at, we used f here, we used f prime here. What are we going to use here? F double prime. Because f double prime tells me the concavity. It tells me if it's positive that we're concave up. And how much positive it is, how big a number is, how fast the slopes are increasing. So it's going to be, if we could use the second derivative as well, we would get an even better estimate. But we have to figure out, all right, now I know what to multiply the first derivative by delta x. But what do you multiply the second derivative by? We're going to wind up figuring this out. So clearly, using f prime prime at x1 will lead to a better estimate. Okay. And let's go on from there. Any questions? Projecting into the future. Using the derivative, but that only sends you along the line, provided, remember we always had to stay, provided we stay in the tangent line. Now if we use the second derivative as well, we don't have to say that. Okay. All right. So now we're going to depart from this, from estimation, to go to this question. Can any function f of x, no matter how complicated it is, be rewritten using only the simplest functions that we know of, which are polynomials? Only using x squareds, x cubes, x fourths, all those different powers of x. My first instinct on this would be, you'd have to be ridiculous. Some functions are way messy and complicated. If the function goes, now it can't double back, you can't do this because that's not a function. But you could have all kinds of, strange things happening, and how are you going to get polynomial functions to do this? Well, actually you can. Now you can't, a second degree polynomial only has one turn, but a third degree could have two turning points. Fourth degree, you could wind up doing a lot of stuff with higher degree polynomials, and then you get to add them all together. All right. In other words, can any function f of x be written as a power series? All right. Note, if the answer is yes, then the task becomes just finding the coefficients, c sub I, for all I. The c sub I may all become 0 after some point, but typically not. Assume that although f is unknown, f of 0, f prime of 0, f prime prime of 0, etc. are all known. Or it may be that f of a, f prime of a, f double prime of a are all known. It may be that a, so this is the variable a, let me make it italics. A represents the present time, and that we are projecting into the future. So not only do you know information like what the value of f is at x1, but you also know what the derivative is, the slope, and then the second derivative, and the third derivative, and you have a whole bunch of information about what's all happening at the present time. And then we want to project into the future. All right. So so here we said, the question, can any function be written as a polynomial? And if the answer is yes, all we got to do is find these coefficients. What we're going to do is we're going to assume that the answer to this question is yes. Let's just assume that it's yes. Assume that any function can be written as a sum of polynomials. Now that assumption is actually a little wrong. Actually, the power series needs to converge to f of x, and we will wind up finding the interval in which it converges, called the interval of convergence, and we'll use one of these tests on it and so on, etc. All right. Then how would we find C0, C1, then C2? How do you find all those coefficients? Because if you can rewrite any function like this, then all you got to do is find the coefficients. All right. So what I'm going to do is I'm going to do this twice. I'm going to do it for the general case. Suppose the function f of x is unknown, and but f and all its derivatives are known. In this case, at x equals 0, and over here it's also at x equals 0. They are known at x equals 0. We're going to change that later on to like x is some other point, like x equals a. Because what we like to do is only project a small amount into the future. And actually, let me just write this at x equals 0 and erase these two other ones. So let me find my right page in my notes. So we're going to start right here. The first thing we're going to do is we're going to find out what f of 0 is. F of 0, it means that x has been replaced by 0. When you replace x with 0, it knocks out every single term except this first one. F of 0 is equal to C0. Or C0, we now know, is f of 0. Okay. Now, we're going to do the same thing over here for sine x. We're going to say, instead of f of x equals this, we're going to say sine x is equal to this. So assume sine x can be written as this power series. Then sine of 0 is going to zero out everything except C0. Or C0 is equal to the sine of 0, but we can actually figure out what the sine of 0 is. A little unit circle, 0 degree angles over here. The sine of that is the y coordinate of that, which is 0. So C0 is 0. Now, when I figure out one of these coefficients, I'm just kind of going to write it in here. And when we get this whole thing, we'll have our power series for sine of x. Now, next thing is we're going to take the derivative of both sides. So we're going to do that for here and for here. And what am I going to come up with when I do that over here? F prime of x. Now the derivative of any constant is 0. The derivative of c1x is you just take this 1 times the c1, x to the 0. And the next one is 2 times c2, x to the first, dial it down, plus 3c3x squared, plus dot 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 dot. Now over here, we take the derivative of both sides. When we take the derivative of sine of x, we get cosine of x. When we take the derivative of the right-hand side here, the C0 derivative is 0, and we know that number was 0 anyway. And then this one becomes just C1 plus 2C2x plus 3c3x squared plus dot 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 dot. Okay. Then we're going to substitute this is true for all values of x. We're going to choose 0. So then we're going to have f prime of 0 equals, now put in 0 for the x, every term over here zeroes out except this first one. Plus, we've just found C1. And then if we put 0 in over here, you get cosine of 0 equals Everything zeroes out. All you get is C1. Thus, C1, what is the cosine of 0? Cosine of 0 is, here's the 0 degree angle, or 0 radian angle, and the cosine is the x coordinate, which is 1. C1 is 1. This thing is 1. Now, I told you earlier, by the time you're done today, we will be able to rewrite sine x like this. And look what we got so far. We got the x term right there. So we got 0 there and then x. By the way, we could be doing this same thing over here. We know that this C1, or C sub 0, we got, what was C sub 0? F of 0. So the general case, it's F of 0. And this C1, we just found out it's F prime of 0. Okay, and let's keep going. Now we're going to take the derivative of both sides. Again, this refers to here and here. Now this C1 could have been replaced with 1, we knew that. This could have been replaced with F prime of 0. So, but it doesn't really matter. If you take the derivative of both sides, what do you get? On the left here, we get F prime prime of x is equal to, now this becomes 0, this becomes 2 C2, there's no x, plus the next one is, instead of writing 6, I'm going to write 3 times 2 C3 x. Can anybody tell me what the next term would be? Anybody see it?
Would it be 2 times 4 C4 x 8?
C4 x to what power?
X cubed.
It would go up by 1.
X squared, sorry, x squared.
X squared. And if we were back here, if I had stuck one more term in, let me just kind of put it in red over here, it would have been 4C4x cubed. And one more term in this one, hold it. Now when you take its derivative, yeah, it would have been 4, see, because it was the x.
So it would be 4 times 3.
Yeah, because this would be, yep. This would be C4 x to the 4th. Okay. So this one would be right here. This 3 multiplies into here, so it's 4 times 3 times this, plus, and then so on. Now the next one after that would actually, if you follow the pattern, look at, this number shows up as the last number. The next one would have been 5 times 4 C 5 x cubed. Okay. And the power on the x keeps getting smaller, like this. And then we set x to 0 and f prime prime of 0. Everything zeroes out, and we get 2c2. But instead of 2, let me rewrite it. It's 2 times 1 c2. And you'll see why I put the 1 in there in a little bit. And so I'm going to depart from the right hand side because I've kind of run out of room. Let's take the derivative again. F prime 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 of x. This term disappears. This 1 shows up right there. You don't get an x. Plus this 2 shows up right here. This 3 is going to show up here. And then we're going to set x equal to 0. Everything is going to disappear. 3 times 2 times 1 is 3 factorial. We keep doing this process. We take the derivative again, and you're going to get a 1 showing up right here. And this 2 is going to show up right here. And you're going to wind up with f prime prime, no, 4s. So 1 1v, the fourth derivative at 0 will be 4 factorial c sub 4. And the number on the prime shows up as the factorial right in front of the coefficient. Right there. We come back up here and we start to see this. Now, when you do this, we wind up putting this, right. So let me erase this thing. So, see now. All right. Let's come back to here. Thus, divide both sides by 2 factorial. C2 is for f prime prime 0 divided by 2 factorial. C3 is f triple prime at 0 divided by 3 factorial. C4 is the fourth derivative at 0 divided by 4 factorial. So we come back up here. It's the second derivative, 2 factorial. This one, it's the third derivative divided by 3 factorial. Okay. And that's the general theory of how we get all these coefficients and turn any function into a power series, an infinite series. And we come over here and let's continue with sine x. I had said before that when we're done today, you're going to be able to do this. So it's going to be x to the x to the third over 3 factorial, x to the fifth over 5 factorial. Alright, let's watch what happens over here. So let me change this color to green here so we can tell them apart. So here, come down over here. Alright, so we have we set x equals 0 and we got c1 is 1. Now we're going to take the derivative of both sides. For this. And the derivative of cosine is negative sine x. And the derivative of 1 is 0. You get 2c2 plus 3 times 2 c3x plus dot dot dot. Now set x equals 0. You're going to get negative sine of 0 everything zeroes out except this one. But sine of 0 is 0. So C2 is equal to 0. So we come back up here. C2, 0. Every other one's going to wind up being 0. Because when you take the derivative of sine and cosine, they do go back and forth between each other. And every time you're on sine, whether it's positive or negative, you get 0. Okay, and that's why that infinite series for sine only had the odd powers of x. Okay, and then we take the derivative again. Okay, and when we take the derivative once again, we get, we're going to take the derivative of this one. The derivative of negative sine is negative cosine x is equal to, now this becomes 0. This becomes 3 times 2 times 1 times c3 plus, now all the other terms contain x. So then when you plug in 0, you get 6c3. Now 6 cosine of 0 is 1. So we get c3 negative 1 sixth, or negative 1 over 3 factorial. And come back up here. That's negative 1 over 3 factorial. And so you're kind of seeing how we get this formula that I told you we were going to get. Minus x cubed over 3 factorial. And so on. And it was a lot that we just covered. But what we've uncovered is this, a Taylor polynomial. All right, let f be a function with f and all its derivatives defined at a. And a might be the present if it's time and we're projecting in the future. It might not be, but it could be. The nth order Taylor polynomial for f with its center at a, denoted p sub n for polynomial, for Taylor polynomial p sub n, has a property that it matches f in value, slope, and all its derivatives up to the nth derivative at a. That is, all these things, the Taylor polynomial will match the original function at a exactly. The nth order Taylor polynomial centered at a is this. And if you stop at some point at n, then it's not the complete Taylor polynomial. The complete Taylor polynomial would be you just take off the subscript of n, call it p sub x, that's the Taylor polynomial, and then you put plus dot 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 dot, and go forever. But the nth order Taylor polynomial is a stop at some point. More compactly, written in summation notation. And it tells you where the coefficients are this. Thus, the Taylor series is this. And this is a big deal. F of x in terms of what's happening at a. Now, the a that we were just using was 0. But it doesn't have to be 0. Plus f prime at a over 1 factorial times x minus a so this is a power series. Well, this one is supposed to be, let me get my eraser side here, is also x minus, oh no, this one was, I was right, f at a plus f prime at x minus a plus f double prime at a over 2 factorial x minus a squared plus, and we keep this pattern going forever. That's this, but it's the Taylor series. And we wind up, like if this was sine of x, we'd put all those different values in there, and this would converge to this function, to sine of x. So any function can be written as a power series of just polynomials, the simplest functions we can think of, whose derivatives and integrals are super easy to take. Any function can be written as a power series if we knew all the information at a, f of a, f prime of a, f double prime of a, etc. Okay. And we can view Taylor polynomials as better and better approximations into the future. Remember when we first started this section, I said, all right, if it was linear, all we need was this first part. But if it's, concave upward, we'd get a better approximation with the second derivative. Well, you can even go beyond that If it's not exactly a parabola, then you would need the third derivative to get even better approximations. Now each of these terms is going to add smaller and smaller portions. They're going to be smaller and smaller corrections. So this is the most important term, and then they get less and less important as you move on. And again, when we actually use them to approximate things, we usually only need about 3 terms or so. Right. But we are very careful that we don't project too far into the future. So if we were trying to approximate f at 16.01, we wouldn't start out with x being 0. We'd start at a being 0. We'd start out at a being 16. And then we would just, be approximating into a tiny bit into the future. All right. We can also view the Taylor series as a replacement for a function which may have been either unknown or something too difficult to work with, something that we couldn't integrate or couldn't solve differential equations that contained that function. All right. So, number 7. And let me pause real quick here. Any questions up to this point? All right. Suppose f of 0 is 1, f prime of 0 is 2, and f double prime of 0 is 1, negative 1. Find the quadratic approximating polynomial for f centered at 0 and use it to approximate f of 0.1. All right. So there's a visual representation I might be interested in here. F of 0 is 1. So we're at this point right up here. The derivative is 2, so the function cutting through this is coming through upward. But also its second derivative is negative, so it was concave down. So although the slope was 2, it was kind of concave down in this region. So it's going up right here, but the second derivative is negative. All right. We use that information when we say find quadratic approximating polynomial. We can go back up to too far. Where were those things? Alright, it wasn't giving them a right. We're going to take this thing up to this point right here. So I'm going to take that. Right here. And find the quadratic polynomial. We're going to be finding p sub 2 of x. And it's going to be f of, now the a is 0, because it's where all the stuff happens. We might view that as the present time, and then we're going to project a little bit into the future. Okay. This is going to be f of 0, f prime of 0, x minus 0, plus f prime prime of 0 over 2 factorial, x minus 0 squared. So p2 of x. f of 0 tells us is 1. So, notice, we are projecting into the future here. But if we project according to the tangent line, we'll get a slight overestimate. So, we are going to be using f prime at a, f prime at 0, which is 2, times x minus 0, which is just x, plus f prime prime at 0, which is negative 1, over 2 factorial is just 2, and then x squared. So, P2 of x is equal to 1 plus 2x minus 1/2 x squared. P2, it asks us to find it, approximate f at 0.1. P2 at 0 plus 0.1. This is my A, this is my delta x. We're projecting into the future from A, like this, is one way you could view this, is equal to, well, when we project into the future, start with the current height. But if you know something about its slope, you know it's 2. Now, if x was increasing by 1, you'd get 2 bigger, but it's only increasing by 0.01, so times 0.1. That, so when you move 0.1 to the right, you're going to move 0.02 up. Oh, yeah, not 0.02, but 0.2 up. And then that makes sense. Now, but we're going to be an overestimate because it was concave down. And that'll be accounted for right here. So then it's minus 1/2. The x is 0.1 squared. Alright, so this is 1 plus 0.2. That's what we would have estimated if we were just staying on the tangent line. But we get this extra little bit of correction. Now this is 0.5, and this is 0.01, so it's 0.005. And so then, I'm going to pull out my calculator. 0.2 minus 0.205 is 1.195. Alright, we have run out of time, and I'm going to finish 11.1 in the first part of class on Wednesday. We only meet for about half an hour, and then you're going to take your test. So I'll finish the 11.1 then. You can just be getting ready for the exam. You don't need to turn anything in 11.1 until it's actually the due date for turning it in is at the final exam, Monday, December 7th. Okay, so the homework is 11.1, turn in by final exam. And if you would stay for a tiny bit longer, just give me a brief bit of feedback. This would be helpful for me in the future with my classes. Anything that you can give me feedback on OneNote and the class videos. Were they helpful outside of class? How did you utilize them if they were helpful, as well as practice quizzes? A little bit of feedback here. You can hit reply to this, go into Canvas, discussions, and if you don't have time to do it now, you could do it tomorrow or the next day. And any questions?
Is it final exam including today's lesson?
Yes. In fact, 11.1 will play a prominent role in the final exam, because that's my only chance to have it in an exam.
Okay, so tomorrow, next time Wednesday, are you going to continue to teach in the 11.2?
No, 11.1 is it. We're going to stop at 11.1, and I'll be able to finish that up pretty quickly on Wednesday.
Okay, thank you.
You're welcome.
Do you want us to start the homework for 11.1, or is it not enough information?
Yeah, you don't really need to. It might give you a little bit better understanding on Wednesday for that first half hour if you start it and do at least attempt a couple problems. That'll make it sink in a little better on Wednesday. But that's all you need to do. All right. You all have a good evening.